Alright, so today we're going to go over some properties of limits, and then I'm going to go over lots of strategies, different strategies in solving limits. So these are some properties. Right? For one, if you have the limit of just some constant k, it just equals k. Right? If you have the limit of some variable x, whereas x approaches a, then it equals a. This isn't anything new, we've done this before. But if you were to have the limit of, say, some function f at x, either plus or minus some other function g of x, you can actually have that as the limit of x at f at x plus or minus the limit of g of x. That works. And you can also do that if you have a constant in the limit. You can pull it outside of the limit if the constant is being multiplied by the function. If you have two functions that are multiplying each other, you can take their limits separately first and then multiply them. That works too. You can do the same thing with division so long as the limit in the denominator does not equal 0. You can see bad things would happen if that was 0. And even with exponents, you can do the same thing with exponents. If you have a function to some power of n, you can take the limit of that function first and then take it to the power of n. So much you can do with limits. So I'm going to go over 6 different examples. Each one is going to be a different strategy. A couple we've seen before, others we haven't. Okay, so let's start with the first one. First one here we have just a trinomial, and we're going to do direct substitution. But before I do direct substitution, just plugging in 2 for x, you can do it right from the start. But I want to show you how some of these properties can work. So first, I can take the limit of each term separately. So I can write the limit as x approaches 2 for 3x squared, and then add the limit as x approaches 2 for 4x, and then add the limit as x approaches 2 for -1. Right? We can do that. That's one of our properties. Another one of the properties says, well, if I have this constant 3 here, I can pull it outside of the limit. Same with that 4. And since this is the limit of just a constant, it just equals that constant. So let me rewrite this as 3 times the limit as x approaches 2 for x squared plus 4 times the limit of x as x approaches 2. And that's just -1. Now what I can also do is first take the limit of x and then square it. So I can write it like this. The limit of x approaches 2 of x, and then I can square that. This one would just be 4, the limit of x, right? That's our other property, so that's 2. As x approaches 2, -1. Over here again, here we have 2, and it's squared, plus, so 4 times 2 is 8, -1, and that's going to all give us 19. Now the next example, we can't do direct substitution. So if I put in 3 in for x, you get 3 minus 3 in the denominator, which is 0. That's bad. So in this case, we're going to try factoring. So you can look at the numerator, and here we have the limit as x approaches 3. So that's a simple trinomial. So we're just looking for 2 numbers that multiply to give us -3 and add to give us -2. So we can have +1 and -3. That works. And that's all over x minus 3. So now what we can do is we can cross those out. And note that because we cross them out, x cannot equal 3. But that's okay, because a limit doesn't say x equals 3. A limit says x approaches 3. It gets very, very close to 3. but doesn't actually equal 3. So we're perfectly safe to cross those two brackets out. And we're left with the limit as x approaches 3 for x plus 1. So we just replace x with 3. And we get 3 plus 1, which is 4. Now the next example is rationalizing. This we've done before. Even in our very first lesson, we reviewed how to rationalize the denominator. But in this case, we're going to rationalize the numerator because we don't want to divide by x, because as x approaches 0, we're dividing by 0 again. So many problems. All right, so the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. So we're going to multiply top and bottom by the conjugate of the numerator, which is the square root of x plus 1 all over the square root of x plus 1, same thing. So we got a difference of squares there on the numerator. So the limit as x approaches 0 would be x plus 1, and then minus 1 squared, which is 1. And that's all over x times that whole denominator there, that whole conjugate, x plus 1 plus 1. Okay, so in the numerator, what we have there is we have a plus 1 and a minus 1. So they're going to go away. And then what we also have then is we're just left with an x on the numerator. But we have that x in the denominator, so they're going to go away. And so what we're left with is the limit of x approaches 0 of 1 over the square root of x plus 1 plus 1. Oh, there's a question in the chat. Is that your dog, Mr. French? Yes, that was my dog. He wanted attention, but he wasn't getting any. So when we substitute 0 now for x, we get root of 1, which is 1, plus 1, which is just 1/2. This is an example of a one-sided limit. So I've graphed this for you. I'm sure you can see that this is sort of half the equation of a circle. Right, it's that positive half. Now if you look at it, if you look at the graph, it says find the limit of this function here as x approaches 3. Well, if we look at the limit as x approaches 3 from the left, so coming from the left, you can see it approaches 0. But what about the limit of x approaches 3 from the right? You can't come from the right. The function doesn't exist anywhere beyond that point. You can probably see that in the square root too. If you were to plug in something greater than 3 in for x, you're going to get a negative number under the square root. So this is not defined. This limit is not defined. And what we learned about limits is if the limit coming from the left is not the same as the limit coming from the right, then the limit does not exist. So in this case, limit does not exist. All right, so this next example is probably one of my favorite strategies. It's a change of variable. So if something looks complicated the way it is, change it. We don't like that x in there. There's like a square root of x on the bottom. So what I'm going to do is I'm going to let some other variable u equals the square root of x. Now if u equals the square root of x, then u squared equals x. And if this function is for x approaching 1, well, let's look at this. U equals the root of x. The root of 1 is 1. So I can rewrite that then as the limit as u approaches 1 of x minus 1, where x is u squared. The square root of x is u, like that. And now that's a lot easier to work with. In fact, from here we can apply that factoring method, because you might see on the numerator, I can write 1 as 1 squared if you like. Doesn't change it. That's a difference of squares. So I can write this then as the limit as u approaches 1 of u plus 1 and u minus 1 all over u minus 1. And again, I can cancel these because the limit only cares about the values approaching 1, not when they equal 1. And we'll get the limit as u approaches 1 for u plus 1. Substitute u in as 1, you get 1 plus 1, or 2. Our last example is an absolute value. So I graphed it for you here, but let's not look at the graph for a second. What I want to do is I'm going to write this on this side. I want you to imagine that this is some function of x, and I'm going to rewrite it as sort of a piecewise function where it's going to have a positive value, not minus, there we go. So you'll have x minus 2 all over x minus 2 if x is greater than 2. So if x is greater than 2, then you can just substitute into that bracket. However, if x is less than 2, we're going to get a negative value in for x minus 2. So I'll just throw a negative out front there. X minus 2 over x minus 2. So I changed this absolute value into two possibilities. If this bracket is going to be negative because x is less than 2, I throw a negative out front there to fix it, because that's what the absolute value would do. It would fix it so it's positive. However, if x is greater than 2, I don't have to worry about that because that bracket's going to be positive anyways. So now if you look at it, we can sort of cancel. So we have x minus 2 and x minus 2. So that's just 1. So the value of this function is just 1 if x is greater than 2. And again here, x minus 2 over x minus 2, but we got that negative out front. So the value is negative 1 if x is less than 2. So now you can probably understand the graph. If x is less than 2, it's negative 1. If it's greater than 2, it's positive 1. So look at the limits then. The limit as x approaches, I didn't write that very nicely. The limit as x approaches 2, let's look at it from the left for our function. Right. Looks like as x approaches 2, the value is negative 1. Equals negative 1. But the limit as x approaches 2 from the right for our function, right, as it's coming from the right, it's approaching the value 1. So because the limit coming from the left and coming from the right do not equal, then the limit does not exist. Does not exist. Emphasize that there.